1-minute warning.
We'll be starting the webinar in about 1 minute.
Okay, let me wave with my hand here. I'm Jim Cahill, and this is Greg McMillan, and welcome to our second edition of Greg's live process control seminar and demo series, and we call these things Deminars for short. Today's topic is PID control of valve stiction and backlash. The broadcast is being recorded and will be available for viewing if others can't catch it live right now. And we've muted all but Greg's microphone, so as questions come up, use the Q&A box to ask questions, and then I'll relay them verbally over to Greg. And we'd like the sessions to be as interactive as possible, so please, as questions occur, send them our way through the Q&A box. And with that, I'll turn things over to Greg.
Hi. This seminar, like the others, are sponsored by Emerson, Xperia Tech, the local business partner in the Midwest, and MINA, who write simulation and apply simulation software for virtual plants. These Deminars and the interactive labs that we're talking about and using were created by me and Jack Ehlers of Monsanto. This is me. My thoughts can be found on my website. I usually make about 3 posts per month, and I've done that for, I guess, the last 4 years. This is my latest book. The royalties are donated to the University of Texas Research Campus for Energy and Environmental Resources. In particular, we're focusing on the development of wireless instrumentation and control. And there is a couple of chapters here that really has the latest information on valve response and smart positioners. So why am I doing all of this? Well, it turns out that I feel like my personal calling and my main motivation in what I do in my profession is to really develop and communicate a deeper understanding of instrumentation, valves, and process control. My 20 books, 50-plus articles and papers, and 100-plus control talk columns are a reflection of this quest. Hopefully, the unconventional cartoons, top 10 lists, and musings provide some insights, breaks down some barriers that open up some minds as only humor can do. However, all of these literary means are static, and I'm ready to take the website, which is an attempt to provide a more dynamic sharing of knowledge, to the next level. My dream is that users would have worldwide access to an interactive learning tool that offers the control room experience to discover, innovate, and generate process control improvements to make plants more efficient and productive. The interactive tool would be a virtual plant set of labs for generic loops, which we're mostly working with in the first few Deminars. And later on this summer, we'll get into the labs for the common unit operations available, such as reaction and neutralization. And the idea is to have these labs available anywhere, anytime, over the web, featuring a non-system specific interface by means of control room type operator graphics. Again, to create and provide that control room experience without relying upon knowledge of a specific type of DCS. These labs will be featuring the power of the DCS, and in particular the PID controller. They'll be featuring performance metrics, for example, integrated peak errors for generic loops, number of communications for wireless measurements, accumulated travel for valves, cost of goods, and profit for specific unit operations. That's the book. And so here's one of my top 10 lists. You know, we enjoy our profession, but sometimes we don't realize some of the benefits besides the enjoyment. So I thought, why not create an Adorable Automators Association? And let's see what some of the possible benefits could be. Number 10, free admission to the Adorable Automators Hall of Fame, the hottest ticket in town. Discounted admission to the Cinemax film, famous control scenes with 3D trend charts. The Automator's alternative Fruit of the Loom underwear, Geek in the Room. Fuzzy is cute buttons for fuzzy logic memorabilia. Dating service, let us automate your pleasures. Simulation services, almost as good as the real thing. Calendar, how about Adorable Automators of the Month? Souvenir t-shirts, my boss went to the ISA executive meeting and all I got was a shirt. Hard hats, that double as extreme bull riding helmets. And how about the #1 benefit of travel discounts to exotic plants? Ride elephants in time. We have a photograph here of Sheldon Lloyd, who's the developer of the I2P transducer and positioner, retired VP of Technology for Fisher Controls. And if you want to learn more about Sheldon, you can check out my Control Talk column in Control Magazine, May 2007, The Best of the Best, Part 5, and here's the link. So let's go to the first demo. And the objective here is initially just to show access to the Cascade Loop Lab setup and how to make load upsets to see the PID response. In Deminar 1, we did the classic thing, was to create set point upsets, but the tuning and performance of the controller changes if the load upsets are what you're really interested in terms of how well the PID controller is doing. So we thought in this seminar we would be doing load upsets to show you the difference. So the activities we're going to access to the Cascade Loop Lab user interface, access the PID faceplate in detail, to the process history view trend chart. We're going to make a load change to show the Cascade Loop response by putting the primary PID momentarily in manual, the key word being momentarily, and changing its output to, say, from 50 to 60%. While that response is developing, we're going to show access to the valve process and measurement parameters for sensitivity, noise, and dynamics. Then we're going to put the secondary PID in auto, and we're going to make a load change to the secondary PID by momentarily, and keyword again being momentarily, putting it in manual and changing its output. So when you first come into the operator graphics, you'll probably get the main graphic here, which shows the initial 5-cell labs that we have. And today we're going to be focusing on the Cascade Loop, so let's click on that. And first of all, we're going to show access to the detail display. So we can click on that little faceplate and then click on the detail icon in the bottom left-hand corner. And we'll kind of move that down here, be a little bit more out of the way. And then we want to get the process history view, and there are icons next to the faceplates here. If we click on those, or one of those, we should come up with the process history chart. If the particular loop lab that you're working with does not come up, you can go to the open folder and select the right one. Right here you can see it's kind of lined out. So let's go back and let's create a load disturbance. And what we're going to do here is momentarily put this in manual. And we're going to increase the output from 50 to 60%. And then we're going to immediately put that back in auto. And while we're waiting for that load response to develop, let's take a look at the rest of what's available in the lab. If you click on any of these blocks in the block diagram, What you come up with is the detail that allows you to change a lot of the options for PID structure. We saw this last week, and you can do it for both the primary, secondary controller. And you can add dynamic reset. You can do what we're going to be doing primarily today. We're going to be adding integral deadband. And you can do what we did last week, which is add in the enhanced PID functionality called PID Plus that was so valuable sampled measurements. For the process, we have our choices of self-regulating, integrating, and runaway for both the secondary and the primary, and we can set the dynamics, the process gain, the delay, lag 1, lag 2. Lag 2 is meant to be the biggest lag, the primary or the largest of the lags, and so that should be kept in mind when you're setting these process dynamics. For measurements, last week we were setting the sample time and the sensitivity. We haven't changed any of the disturbances. They're important when you actually go into the test and run mode. And you have the control valve here, and today we are setting stick slip and deadband for the control valve. Well, let's see what's happening to the process response. And the demo is designed to be fast, so we don't have to wait a whole lot of time. So we need to decrease the time span. We can do that by clicking several times on that button, and then we're going to have to scroll forward to find our response. If we look at the primary process variable, the dark blue, we see that it hesitates a little bit coming back to set point, but there is no undershoot. It's not tuned perfectly, but it's tuned reasonably. On the secondary process variable response, which is being driven because we're operating a cascade loop, we see that it is undershooting a little bit, and that generally is okay for a secondary process variable because it means you're getting a faster response, which is good for what you're most interested in, which is the primary process variable. So that helps the primary process variable get back to set point quicker. Now that we've seen a cascade response, let's take a look at the secondary controller. So let's bring up its detail. And we can see it's in cascade mode. Click on that lower icon to get the detail. And let's bring back up our options on dynamics, and let's create a disturbance in the secondary controller. But in order to do that, let's take it out of cascade. Let's put it in automatic. So we're going to look at how the secondary loop behaves on its own at set point being corrected by the primary controller. So now we're going to create the secondary disturbance, low disturbance, by momentarily putting it in manual and changing the output to 60%. Again, put it back in auto, and we'll wait a little bit to see that response develop. And while that's happening, let's go back to the seminar slides. While we're waiting for the response, we have a question. What oscillation cannot be eliminated by PID controller tuning? We think we generally can kill an oscillation if we tune the controller slow enough, but there are some oscillations where you can't tune it out. What is the most common cause of a sustained oscillation? What response problems are not seen in tuning tests? By open loop tuning tests, I mean you're putting the controller in manual and you're stepping the controller output, and you're then looking at the response of the process while the controller is in manual. What don't you see in terms of potential response problems when you do that type of test? What creates a dead time inversely proportional to controller gain? What problem became rampant in the 1980s in a quest to reduce the cost of field instrumentation? And what is the biggest hidden menace to loop performance? Well, the answer is valve backlash and stiction. And that's the focus of our seminar today. So next we're going to compare the base case to a scenario where we've added 5% stick slip on the response. See what happens then to the response of the secondary PID in the auto mode. But first, we'll look at the load response of the PID for the base case. We will keep the secondary PID in auto, and we'll increase the valve stick slip. And then to create a disturbance, we will make a load change to the secondary PID. So let's look at the response here for the base case, and we can see that we're getting pretty good response in terms of the secondary controller in orange coming back, although there's a little bit of oscillation from this load disturbance entering into the secondary loop. In other words, by having the disturbance coming into the secondary loop, it's more disruptive and therefore creates more of an undershoot, and it takes longer to recover. So we're going to keep the secondary loop in automatic, and we've got the option now of increasing the stick slip, and so the base case didn't have any, but now we're going to add 5% stick slip, and we're going to make a load change, which is done by momentarily putting it in main and changing the output and making sure you put it right back in auto. And while we're waiting for that to develop, let's go back to our seminar slides. Let's look at what the causes and nature of this problem that we're going to be focusing on, which is stick slip and deadband. And what we have here is a plot of stroke versus signal, and we have taken the signal all the way from 0 to 100% and then back from 100% to 0%. And the official definition of deadband would be exactly that, in terms of making a 0 to 100% signal change in the up direction and then reversing it and going from 100% to 0%. And the change in signal that you have to make before you actually start to reverse the direction of the stroke is the deadband. And while that's the theoretical definition of deadband, it turns out whenever you need to change direction of the control valve stroke, the signal goes through a deadband, and this is principally caused by backlash. And in actuality, the deadband tends to be worse near the closed position. The other thing that we have that's a response problem is stick slip. And here, no matter what direction you're going, and here we're showing increasing signal, the valve doesn't respond to a small change, a relatively small change. When it does, it jumps. And so what I got shown here is kind of like a staircase. It sticks, slips, sticks, slips. And I've only shown it right here at the beginning. But while this is generally worse at the closed position, it can occur throughout the whole stroke in both directions. Pneumatic positioners required a -% signal to close the valve. This is because the position calibration could not be that exact to begin with, and within a few months it tended to drift. And you didn't have position feedback, so you didn't know about it. So there was a lot of uncertainty as to whether that valve was really closed or not. So what we did is added a low limit that was maybe -10%. And so we actually allowed the controller output signal, which was going to the valve, to go to a -10% to make sure that that valve was closed because of, again, the uncertainty in what the actual position was and the problems with the drifting of the pneumatic positioners. Then we got digital positioners, and they forced the valve to be shut at 0% because they had a much more precise calibration, plus they held their calibration. And so electronic digital positioners eliminated the need for a -10%. And then we used smart ones. We got in a little bit of trouble initially in that if we kept in our old output limits of a -10%, there was not enough power at the low milliamp signals in some cases to keep the smarts going. And so those positioners, at least in terms of maybe their diagnostics, went to sleep until the signal and the milliamps got high enough to provide the power needed. Well, and the other thing is, by eliminating that -10% limit, you could get the valve off of its seat quicker, even though you have anti-reset wind-up limits that are helping you move through that region of -10% to 0%. Still, you're going to be a lot quicker if you don't need to set your low output limit at a -10%. Now, if you didn't have a positioner, and there was a case where for fast loops back in the 1970s and 80s when we had primarily electronic analog controllers, there was a case maybe where we could get into some difficulty with a pneumatic positioner and an electronic controller. And as a result, there was a rule that on fast loops shouldn't use positioners, but this unfortunately created dead bands of 5%, and I have even seen almost 50% for some particular valves. And so we're fortunate today in that all loops, whether they're fast or slow, should have positioners because of the speed of the digital positioner, and the tuning options eliminates the concern that we had way back when with pneumatic positioners. So to summarize, deadband is a change in stroke, change in signal, to reverse the direction of the stroke. The principal source is links and mechanisms for rotary valve action. So if you have a rotary valve where you're rotating a ball, a disc, sometimes you even rotate something called a plug, then you're much more at risk for deadband from backlash. The stick slip is the smallest possible change in control valve stroke. The principal source is friction and packing and friction in the closure element and the seal around it, the seal around the ball, the seal around the plug, the seal around the disc. The tighter the shut off the valve is, generally the more the friction is and the more problems you have there. It can be seen as shaft wind-up and breakaway in rotary valves. There can also be some friction in piston actuators that are not properly lubricated. There's also sensitivity limits that we're not be talking about here, but while they're much smaller, they can still be a concern, and they are a limitation, and they're usually associated with piston actuators and pneumatic positioners. And they create a staircase response similar to stick slip. And as I mentioned, valve deadband and stick slip is the greatest near the closed position. Well, next we're going to compare the slow versus fast tuning effect of the secondary PID on its response to 5% stick slip. But first, let's look at the limit cycle in the secondary PID for 5% stick slip for the fast tuning, and then we're going to increase the PID reset time for the secondary control loop, and we're going to go from 2, say, to 10 seconds to show the effect of slow tuning. Well, we got a limit cycle here. And classic definition of a limit cycle, at least for me, simplistically, is that it's a nearly constant amplitude oscillation. Now, I don't have any disturbances in here. In real life, there would be some disturbances, and so the amplitude would vary. In fact, the whole oscillation may shift up and down. Aided a disturbance to start it. If there are no disturbances, it would take quite a while for this oscillation to develop from a very tiny error between the process variable and the set point. And so we can look at this thing, and we can take a look at the second primary process variable in dark blue, and we can see that the amplitude is about maybe 1.5% from its set point. We can look at the secondary loop process variable, the orange, and we can see that actually its amplitude is a little more than 3% on the high side, and on the low side it's more like 2%. So it doesn't need to be symmetrical about the set point. And the thing is, we can't tune this out. If you slow down the tuning, it's not going to disappear, but it may affect it. So let's see what happens there. So to slow down the tuning, we're going to change the reset time to 10 seconds. And while that response is developing, let's go back to the Demonar slides. Now, I mentioned that a lot of the backlash does come from rotary valves, and what I'm going to show you is the four common types of actuator rotary valve setups that create this backlash problem, and to varying degrees. And the principal problem is you're converting from a linear motion in the piston actuator to this rotary motion of the ball or disc or plug called the closure element inside the control valve that's actually determining the throttling area available for flow. And so we have what's called a direct connection, but you notice that there is still a linkage here, and there is a translation of movement that creates a moment arm that's varying with crank position. Then there's a link arm connection to the rotary valve, and now we have a couple of pins. And wherever there are pins, there are opportunities for backlash. The rack and pinion actuator eliminates those links, but it has these gear teeth. And as a result, there is a resolution limit associated with that. In other words, you can't make a finer adjustment than what is allowed by those gear teeth. Plus, these teeth can become worn, and you might actually slip between a couple of gear teeth, causing a greater slipping action and jumping of position. The Scotch yoke actuator has particular problems, and again, through this pin here and the slot creates quite a bit of backlash. So not shown here is the preferred solution, which is a splined shaft and a diaphragm actuator and rotary motion that eliminates the needs for this translation and linkages or slots and teeth that we see in these previous slides. And so there are much better ways of doing rotary control valves, and these principally are done by the companies that started out designing rotary valves for throttling service. What we have here in these last four slides is the attempt to take a piping valve designed for on-off service and put a relatively expensive piston actuator on here and create what you think is a throttling valve, but the end result is you have to deal with the backlash and deadband consequences. And then if you look at the fact that the tight sealing, tight shutoff, low leakage, very low leakage associated with these piping valves create excessive seal friction, we end up with additional problems in terms of stick slip for these piping valves that are used as rotary valves. And this became very popular in the 1980s and 1990s because it looked like a cheap solution. The piping valves, gosh, they did great as piping valves, as isolation valves. But that usually means they don't make good throttling valves. And so spending the extra money to go to a control valve manufacturer and get a real throttling valve was something that was often not done on projects in an attempt to save money. So let's go back to the demo. Next we'll want to see the effect of the secondary PID I-deadband option on the limit cycle and the P auto mode for the 5% stick slip. But first, we're going to look at the limit cycle in the secondary PID that we have now for slow tuning. Then we are going to put the I-deadband setting at 4% and see what happens then. Well, by increasing the time, slowing down the tuning, we didn't change the amplitude, but we did make the period of the limit cycle longer. Now, this might seem like it's okay, but what happens is it creates bigger problems in the primary process variable. And if you take a closer look here, notice the amplitude of the primary process variable. We said it was maybe a little over 1.2, 1.3%. Now, because of the slower cycle and the fact, it got a slower oscillation and the filtering effect of the primary time constant there is consequently less. Now we've gone from an amplitude of 1.2% to over 2%. And so by slowing down the tuning of the secondary loop, which you might think is the right thing to do to try and kill the oscillation, actually is the wrong thing to do here on the primary process variable. But also in general, when you look at the fact that we're trying to filter out oscillations by taking advantage of process volumes downstream, particularly those well-mixed volumes and tanks, and the slower oscillations, just, from circuit theory in terms of electronic filtering of oscillations, the slower the oscillation for a given time constant, filtering time constant, the bigger the amplitude. And so in general, if we're going to have a limit cycle, we would like it to be as fast as possible. So let's go back and we're going to set that reset setting back to where it was at 2 seconds. And now we're going to see, well, what can we do to maybe kill that limit cycle? And we do have an option in the P controller called integral deadband. And what this does, it stops the integral action if the process variable is within that integral deadband of the set point. In other words, if the error in the process variable is less than the I-deadband, and it works on both sides of the set point. If the absolute error is less than the I-deadband, it stops the integral action. Now, you still have proportional and you still have rate action, so if you had disturbances, you won't see a straight line. There'll still be some movement of the controller output and the process variable as the proportional and derivative modes respond to those disturbances. But I haven't turned on the disturbances here. So let's put in the secondary PID I-deadband of, say, 4%. And what you want to do is take the maximum deviation, which we saw was like 3%, and add at least 1% to it, because disturbances are going to shift that oscillation to be more on one side than the other. And I guess technically it's probably the safest setting, if you knew that the stick slip was 5%, would be a 5% setting. But we'll go with 4% here. And while that oscillation is seeing the effect of an interval deadband. Let's go back to the demo slides. Now what I've got shown here is the installed characteristics for two of the most popular types of trim. The first one is linear, and so the dark blue diamonds are the inherent characteristic, and this is for the situation where the pressure drop across the valve is constant. It means that most likely, in terms of the system pressure drop, nearly all of it is across the control valve and very little of it is in the piping system. However, let's look at the effect of the fact that maybe the ratio of the pressure drop allocated to the control valve is like 50% of the total system pressure drop. So we have frictional losses occurring in fittings and piping and equipment that's in line with the control valve. And so that's our red squares here, and we see that it starts to deflect upwards. Now, in an attempt to save energy, we are driven to allocate less and less pressure drop across the control valve. So we move to the extreme case, and it has been cited that you could possibly go with as low as 5% of the total system pressure drop is allocated to control valve. We end up with this purple cross curve here, and we see now that we have what looks like almost like a quick opening characteristic, and in particular we're getting into some concerns here right at near the closed position, and that if we're looking at signals less than 10%, and maybe what's happening there in terms of stick and slip, we're finding that we're getting changes in flow that could be quite large. And in fact, there could be a magnification of about 10 or 5 to 1 in terms of the actual UC. So quick opening characteristics are generally not advisable for systems. There is some cases where you could say you want that maybe for surge control, but in general, the quick opening characteristic causes problems in most control loop applications. So let's look at actually the more common choice in trim, and you might think, oh, well, I don't want this because I'm introducing a nonlinearity. And for the inherent characteristic where you are allocating nearly all of the pressure drop in the system to the control valve, you do have this equal percentage type curve. But notice now as you move towards allocating less of a pressure drop across the valve, and say considering the black triangle case, what we're getting into is a more linear throttling range in the area of greatest interest generally, which is say between 40 and 70%. And then as we get into saving energy, and we go for like the of which I'm not sure I advocate, of 5% allocation of the system drop to the control valve, we actually have some nice linearization here, but now we have a problem, and that as we can see here, that there's quite a bit of flow when the valve is almost closed. Now, in most equal percentage valves, it wouldn't probably be as bad as it's shown here, in that the rangeability would be greater than 50 to 1 that I've plotted here for the inherent characteristic. So this is, this is not as really the case for a good throttling sliding stem valve. But just to kind of show the effect, I think it's useful to see that we are going to have somewhat of an issue as we get into stick slip near the closed position in terms of what it means in terms of a change in flow. Well, let's see for our next objective the effect of a secondary PID deadband on the limit cycle in the CAS mode for 5%. But first we'll look at whether we were able to eliminate the limit cycle in the secondary PID by use of the deadband in the secondary PID for this 5% stick slip while it was still in the auto mode. Then we're going to secondary in the PID mode, secondary PID in the cascade mode to see, what's the situation there? Do we still have this smooth response by just having the deadband in the secondary controller? Well, we can see that putting the deadband in the secondary loop when it's an automatic has killed the limit cycle, but there is an offset, and so that's the price you pay. Now, that offset may be not as much a concern in that loops, say, that are downstream might be able to correct for that offset by the things that they do in terms of their control action. And in general, the most disruptive type of an upset is a periodic one. If you have an upset that comes in and then just stays at a constant value, control loops downstream can deal with that. So in general, this is in terms of eliminating frequent disturbances downstream. So let's see what happens now if we put that secondary loop in the CAS mode. And while that response is developing, let's go back to the Deminar slides. There's a lot of statements on rangeability that are made, and I think an awful lot of them are very misleading because the piping valve manufacturers, when they're selling you a rotary valve, it has a high flow capacity. Particularly if it's a full bore ball valve, and so you've got like the whole cross section of that valve available for flow, or it's a butterfly disc valve, and it's 90 degrees open, and except for the disc, got that whole pipe available for flow. You've got a tremendous high flow capability. And if they don't really take a look at the effect of stick slip or deadband even near the closed position, they'll come up with rangeability numbers of 500 to 1 or more for these piping valves. The real rangeability, to me, depends upon the installed characteristic and also how much stick slip there is at near the closed position. So that's what these equations do. I've developed these equations. I've never seen them anywhere else. I think they do provide a practical way of viewing the real rangeability of your control valve. So for linear valves, you can come up with a minimum C sub E based on the stick slip, and you can do that also for equal percentage valves where R is the rangeability. For the plots I mentioned, the R I was using was 50 to 1, but I think in general sliding stem valves have R's of from a control valve manufacturer, say 100 to 1, so that might be a better R value to use. Once you have the minimum flow coefficient expressed as a fraction of the maximum, you can substitute it into this equation for the installed characteristic and come out of that with a fractional minimum flow. You can then take that and you'll get your real rangeability of the control valve. Our next objective is to see the effect of deadband in both the primary and the secondary PID when we're in the cascade mode for 5%. But first, let's look at the creation of the limit cycle in the secondary PID for the 5% stick slip now that we are in the CAS mode. And then we're going to set the primary PID deadband to 4% to see if we can make things better. Well, notice now that we've put the loop in cascade, having the deadband and just the secondary controller does not kill the oscillation any longer. We've got the oscillation occurring because now the primary controller is doing its thing in the cascade mode. So we need to add integral deadband to the primary controller as well. And to give it a little leeway there, we'll put in the 4% as well. And while we're watching, wait that response to develop, let's go back to the Deminar slides. Now, we did take a look at the effect of fast and slow tuning, and we principally saw from changing the integral action of the secondary loop while it was in the auto mode, that we could see that there was no effect on the amplitude, but there was effect on the period of the oscillation. And the reason for that is the amplitude of that limit cycle is based on the process gain. Now, I like to use a parameter that has a little more detail than saying the process gain, although, I mean, that's what's out there. Everybody says process gain. Well, really, what we have in a control loop is a product not only of the process gain here, associated with the unit operation, but also the gain associated with the manipulated variable, principally the control valve. So in this case, it's the slope of the installed valve characteristic is our gain for our manipulated variable. We've got the process gain we normally think of, and that's based on the unit operation and the process variable of interest. And then the PID controller works on signals in percent. So we got to take the measurement and convert it to percent. So there is a scale, calibration and scale for that measurement, and that creates a measurement gain. And so what I say, a better term, is the open loop gain. In other words, if the controller is manual and you made a change in the controller output and you multiply that change in controller output by this open loop gain, that's what you would see then in terms of a percent change in your process variable. If you take that into account here, because it does also enter into the equation here along with controller gain, we can see that we can affect the not the amplitude, but the period of the oscillation. What we did was change the interval time. We increased the interval time, the reset time, and so we saw a increase in the period of the oscillation. So the next objective is to see the effect of valve deadband. We've been looking at stick slip, but now we're going to see the effect of valve deadband on the cascade mode with no I deadband and either the PID, and we're going to be putting in 5% valve deadband. But first, let's look at the cascade loop response with 5% stick slip, which is where we left off, with existing deadband, I deadband settings of 4% in both PIDs, and we're in the cascade mode. And then we're going to set the stick slip to 0%, and we're going to introduce a valve deadband. And we're going to affect the PID, I deadband, integral deadband out by setting those to 0% in both controllers. So now that we've put the integral deadband in the primary controller so that we got it in both the secondary PID and the primary PID, we have again killed the limit cycle and we have an offset. And that is preferable in most cases in terms of loops downstream and their ability to compensate for this disturbance. So now let's go and look at what are the effects of valve deadband instead of valve stick slip. So we go with control valve, and we'll take the stick slip out. We'll put the deadband in. And we'll go back to the PID. We'll take out the integral deadband. And we'll see what happens with that response. But instead of watching it, let's go to the seminar slides. Talk a little bit more about how you really test a control valve. And one of the things that is a common problem, and that dates back to the 80s and 90s, is that we tested control valves by introducing, say, a 50% signal, and somebody go out to the field, and we didn't have position feedback, so we thought, oh yeah, it looks like it's about half open. Then we put the signal at 100% and said, oh yeah, it looks like the valve's fully open, and then we thought we had checked out the valve. Well, if you look at what's happening from one module execution to another, hopefully the output is not changing by 50%. If you have 50% changes in your output, almost any valve, even if it doesn't have a positioner, is going to respond. And maybe it's slower for the big valves, but you're not going to see really the effects of backlash and stiction, and in particular some other issues that arise in terms of sensitivity as determined by the actuator and positioner. And so what we have here from actually the ISA standard on response testing for a control valve is a nice plot that for various valves, and I think these are probably for older positioners, that shows that if you decrease the step size below 1%, some valves right away, the response, like this one over here, deteriorates. And in general, as you move to smaller step size, say like 0.4%, a lot of these valves can take about 10 times longer to respond. And this is the result of a sensitivity limit that's possibly in the actuator, maybe it's a piston actuator, or in a pneumatic positioner typically. Our next objective is to see the effect of valve deadband in the auto mode, right now in the CAS mode, with no iDeadband setting in either PID. So first we're going to look at what has been happening in the cascade loop response with the deadband. Again, any integral deadband on the PID, but we do have a 5% valve deadband, and we're operating in the cascade mode. Then we're going to put the secondary controller in the auto mode and see what happens. So we can see here that we do have now an oscillation from the deadband. And one of the reasons why I chose to show this demo is because there is some misinformation out there, some rules that said, well, if you have valve deadband, you're not going to have a limit cycle in a self-regulating process.
Switch sharing over.
And I forgot to switch over sharing, so you're not seeing that yet. Sorry. Thanks, Jim. So here we see that there is an oscillation that's broken out, and because we're in the cascade mode, and so the message here is if we have the deadband and we're operating in a cascade mode and we have interval action taking place in the secondary and primary loops, they're going to cause a limit cycle from deadband. Which is contrary to maybe what the popular understanding is. Now, if you just had a single loop with a valve deadband and it was a self-regulating process, then the conventional thinking is right. And so to check that out, let's go and change this secondary loop to the auto mode. And while that response is developing, let's go back to the demo slides. So the best solution is really not to create significant backlash and stick slip. I mean, we saw how we can use integral deadband and the PID to help deal with the situation. But the best solution is to get a good valve, good throttling valve. And so in particular, we want an actuator valve and positioner package from a control valve manufacturer. We want a digital positioner tune for that valve package and that application. There's a lot of tuning options and tuning capability in digital positioners. We want diaphragm actuators because they have the greatest sensitivity. When we weren't looking at step sizes below 0.5%, we thought piston actuators that were fine. But it turns out if you really want to respond to small steps, a diaphragm actuator. However, for large valves and high pressure drops, you may need to go to pistons, although now some diaphragm actuators have higher pressure capability, which extends the pressure drop and size capability where they're applicable. So if possible, you go with the diaphragm actuator. Also, if possible, you go with sliding stem globe valves where the size and fluid permits. If you get into very large flows and slurries, these require rotary valves. If you have to have a rotary valve, the best one is a low friction V-ball type or a contoured butterfly. And these valves were originally designed for throttling. I've gotten a lot of confusion about this in that there are V-notch balls, but they were originally designed for piping valves, and they actually have a horrendous response. In one case, it was actually out of the catalog. It showed that there was no response in flow for the first 40% signal going to the valve. So once you get into rotary valves, you have to be very careful, and I think the best thing I have as advice is make sure that rotary valve was originally designed for throttling service and not as a piping on-off or isolation valve by a company that was in business originally to make piping valves. Use low packing, sealing, seating, and actuator friction. If you need to speed up the response, put the boosters on the positioner outputs. We'll go into this next week for large valves and fast loops, for example, for compressor anti-surge control. Do a good job of valve sizing to provide a throttle range that provides the best linearity of the installed valve characteristic. And typically this is 5 to 75% for a sliding stem globe valve. That's a good throttling range. 10 to 60 degrees for a V-ball valve, 25 to 45 degrees for a conventional butterfly, and 5 to 65 degrees for a contoured and toothed butterfly valve designed for throttling service. Online diagnostics and step response for small changes in signal, and we're going to get into next weekly using dynamic reset limiting with digital positioner feedback. Okay, our next objective is to see the effect of valve deadband on an auto mode response of a high gain PID for an integrating process. But first, let's look at the single loop response with 5% valve deadband. And again, we have no integral deadband in these PIDs. And we're in the auto mode, and we're still a self-regulating process. Then we're going to change the secondary process to integrating. To prevent some instability, we're going to have to make sure the order of the following steps is followed. First, we're going to make sure that the secondary PID is an auto. We set the secondary process lag 2 to 20 seconds from its current value of 2 seconds, and we set the secondary PID reset time From its current value of 2 seconds to 100 seconds, we increased the PID gain to 5, and then we can switch the secondary process type to integrating. And we can see that if we're out of the cascade loop mode and we're just have us with deadband, there is no limit cycle. And that's what people were saying out there, but they should have qualified what they're saying and said, well, that's true for a single loop. You go to cascade mode and the limit cycle is going to develop for deadband. All right, well, let's go on to integrating processes, and I know we're kind of running a little short on time. We're going to go over a little bit. Hopefully that's okay. If you have to sign off, basically you've seen the effect of various cases in a self-regulating process, and what we're going to show for the integrating process is that deadband in itself, whether you're a single loop, cascade loop, or any type of loop, it's going to develop a limit cycle if you have a type of integrating. Well, we're checking here that the secondary loop is in auto, and now we're going to change the process lag here for the secondary loop to 20 seconds. Whoops, that's the wrong one. I want the lag 2. Change that to 20 seconds. Then we're going to change the secondary reset setting to 100 seconds. We're going to set the secondary PID gain to 5. And now we're ready for the big change in the secondary process to integrating. And the control valve still has 5% deadband, and we're in the single loop case because we're in the auto mode. While we're waiting for that response to develop, let's go back to the Deminar slides. And to interject a little bit of humor, here's the top 10 signs. Your control valve is an on-off valve in disguise. The valve body looks suspiciously like the block valve next to it. The actuator looks suspiciously like the one on the safety instrumentated system valve. Process engineer is seen going to lunch with the piping valve supplier. The valve deal is a steal. Your flow is on-off. The positioner measures actuator shaft instead of the ball or disc stem position for feedback. Oscillation amplitude exceeds the largest historian compression setting. 360-degree feedback in your loop becomes 360 feedback in your performance review. The valve package is nicknamed Sloppy Joe. There's no valve leakage, even with a controller output of 40%. So our next objective is to stick the valve deadband on the auto mode, but with a slower tuning of the controller for the integrating process. But first, let's look at the single loop response with 5% valve deadband, high gain PID for the integrating process. Then we're going to change the PID gain from 5 to 1. Well, notice we've got a limit cycle. We can see it most evidently in the sawtooth of the secondary controller output. And I forgot to switch over to the desktop. And we can see the sawtooth most evidently in the controller output. And we have to look pretty close to see it in the process variables, but it is there. And principally, because the reason why it's so small in the process variables is because we have the higher controller gain. Let's see the effect of lowering that controller gain from 5 to 1. And while that response is developing, let's go back to the Deminar slides and see if we can wind up what we're trying to about. Well, this shows that we can predict the effect of controller tuning and in particular on controller gain on the amplitude of the oscillation. We will see that the amplitude, in this case of the limit cycle, will change with controller gain. And we'll see that the period of the oscillation will also change with controller gain. Notice that period oscillation not only is affected by controller gain, but also by interval time. As a summary, for valve stick slip, the problems are it adds dead time, inversely proportional to the PID output rate of change. Therefore, if you have slow tuning, you're going to get more dead time from stick slip. It creates a limit cycle, persistent constant amplitude oscillation in any PID that has integral action. Slower tuning increases the period but has no effect on the amplitude. Integral deadband must be added to both the secondary and primary PIDs to eliminate the limit cycle in a cascade control system. For valve deadband, it adds dead time inversely proportional to the rate of change of the PID output, like was the case for stick slip. So slow tuning does add more dead time from deadband. There is no limit cycle for a single loop on a self-regulating process. However, it creates a limit cycle in cascade loops. It creates a limit cycle in integrating processes, and we're not going to show it here, but also for runaway processes like on an exothermic reactor, which would be particularly bad news. In fact, you could, if the limit cycle got large enough, it could just run away from you. The limit cycle amplitude and period are inversely proportional to the PID gain, although it does vary with the power in terms of the period effect. PID solution, regulating processes add integral deadband to eliminate limit cycle, but you create an offset, but that's easier for downstream loops to deal with. For all types of processes, we haven't discussed this, but I will put it out on my website, some test results for deadband and stick slip compensators or the use of the lead lag on the PID output. And this can reduce the dead time and increase the frequency of limit cycle of the secondary loop, which will increase the filtering in terms of what the primary process variable sees or downstream loops sees. But it does increase the amount of valve travel, and it's going to wear out packing and seals. So I'm going to go back to the demo and see what happened. And now we've got a much slower oscillation, but also notice the amplitude in terms of the process variables has gotten larger. And so we've created more of a problem in terms of a slower and bigger oscillation by decreasing the controller gain. So let's go back and wind up the Deminar.
All right, I'd like to first thank Greg for sharing his wisdom with us today, and I want to open up the floor to questions, and you can enter those in the Q&A box if you would. But first, we'd really appreciate it if you could spend a minute to answer a one question and comment survey. And you'll see on the link, here's the URL to go to the survey. It's just wouldyourrecommend.us/105679S21. And would really appreciate your feedback. It helps us with the future ones that we have scheduled. Okay, our next Deminar is going to be May 12th, same time, 1 p.m. Central Daylight, which is UTC -5. And the subject of Greg's talk will be PID control of slow valves and secondary loops. And for those of your friends who may get some benefit from these, this session's being recorded and will be available on both our blogs, on Greg's modelingandcontrol.com and on mine, emersonprocessexperts.com. So look for the recorded version, and we ask you to help spread the word if you think others would benefit from these. Okay, and finally, are there any questions in the last few minutes here? Oh, I see a couple in here. Let's see. Harley asks, would you be able to expand on your comment regarding use of deadband with oscillatory disturbances?
Well, I think if you can see the trend in terms of what the maximum deviation is of an oscillation from the set point, then that would be the integral deadband setting, but you'd have to add in a little bit extra leeway there to account for noise, which I don't have really added in, although you could add into these labs noise and disturbances. I think in real life, you look at the trend charts, and it's not so straightforward as it's seen here because of you've got noise and disturbances shifting things around. So you almost have to maybe do some statistics or visualize what are the short-term repetitive cycling that you've got going, and what is the maximum amplitude of that in terms of the error, the absolute value of the error of the process variable, and you got to make sure your integral deadband setting is larger than that. And even if it doesn't capture, stop the limit cycle all the time, in other words, the limit cycle might start and stop because I have really no assurance that the valve deadband is a constant variable. It's going to change with operating point and with valve age and wear and tear and maybe maintenance, and so valve deadband is not constant, and I think you might have to periodically adjust this. You could envision maybe something to do this adaptively in terms of automatically adjusting the integral deadband to kill the limit cycle.
And Deepak, did you have a question? I'm looking on it. Don't see the question coming through. You, or if anyone else has a question, put it in there. All right, well, I want to thank everyone for joining us today, and we'll get the recording of it, so look out on our blogs within the next day or two, and we look forward to connecting with you at the next one. Thanks a lot.
Thank you.